Okay, so I'd like to just walk you through the fifth problem from the handout for tangent planes and linear approximations. So if you've got that handy, it says a company manufactures cylindrical aluminum tubes to fit rigid specifications. The tubes are designed to have an outside radius of 10 centimeters, a height of 50 centimeters, and a thickness of 0.1 centimeter. And then it goes on about the manufacturing process errors. We'll bring that up again momentarily, but the first thing is to find a formula for the volume of the material used to construct such a cylindrical tube. So let's take a look at what one of these tubes would look like. And so if we take a quick look here, we've got sort of a tube like this, and it's got a radius up at the top of R, and then it's T thick along the way here, and then the height of that tube is going to be h centimeters. And the way that I think about finding the volume of this is that if we had a solid cylinder rather than a hollow cylinder, then we'd have a volume that comes from pi r squared h as our standard volume of a right circular cylinder. So we've got that. Now if we think about the inner part that's missing, we could subtract off that. Well, that's a right circular cylinder as well. And so the radius of that is r minus t, because the radius of the whole thing is r, and then you've got to ignore the t portion that's sitting out there on the edge. And so then this leads us to the missing volume is pi times h times r minus t quantity squared. And from there, we can just subtract the volumes and a little bit of algebra to make this a little bit nicer to work with. There's a pi h in common to pull out, and then squaring that allows the r squareds to cancel out nicely, and so we wind up with finally pi times h times, there's a t in everything, and then 2r minus t. Okay, so now we can get at the actual manufacturing. We're supposed to use differentials to estimate the maximum error in the volume of a tube. And so to do this, we're going to, as the question says, use differentials. Well, to use differentials, we're going to need some partial derivatives. So let's just bring over the volume formula. This is actually a function of three variables, r, h, and t. As the handout said, we can do the same idea for linear approximation here as we do for two variable functions. We just do it for each of the three variables, which means we're going to need the three partial derivatives. So the partial derivative with respect to h, pretty simple, is pi times t times quantity 2r minus t. And then we'll do the partial derivative with respect to r, which is just 2 pi ht. Partial with respect to t, little more work. 2 pi ht minus 2 pi 2 pi hr minus 2 pi ht, which then is 2 pi h times the quantity r minus t. Okay, so in our formula for the differential, which will be dv, we need to evaluate these partial derivatives since we know what the specifications for r, h, and t are. So we're going to evaluate these at r is 10 centimeters, h is 50 centimeters, and t is 0.1 centimeters. And I'll just gone off and done these separately for you. You substitute these in, you get that VH is 1.99 times pi, VR is 10 pi, and VT is 990 times pi. So now let's write down the differential here. So dV is the partial with respect to r times dr plus dVH times dH plus the partial with respect to t times dt. And so now, as we look at this, notice that the partial with respect to t is 990 pi. It's huge. It's almost 100 times the partial with respect to r. So a corresponding change, so if the error tolerance on the thickness were the same as the error that we could, the manufacturing error we could have in the height, this would be a dramatically bigger impact on things, just that small increase in the thickness, if it could be as large as the radius or the height. Fortunately, the maximum error on the thickness is much smaller. And so now we can come in here and we can put in our 10 pi, and dr, we're told in the problem, is that the maximum error on the radius and the height is 0.05, plus or minus 0.05 centimeters. And since we're asked to find the maximum error, that means we're going to put in the largest that the error in the radius could be. So we'll put in 0.05. Then we'll put down the VH. Also the maximum error in the height is 0.05 centimeters, so we'll put that in there. And now we'll bring in our VT, 990 pi, and then we've got 0.0005 centimeters. And so calculate this out, you get a maximum error in the volume of approximately 3.44 cubic centimeters.